Hello, friends. Have you ever wondered about the strangest phenomena in the universe? Quantum entanglement, a concept so bizarre that even Einstein called it spooky action at a distance, is one of the weirdest and most fascinating aspects of quantum mechanics. Quantum entanglement is a phenomenon that occurs when pairs or groups of particles interact in ways such that the quantum state of each particle cannot be described independently of the state of the others, even when the particles are separated by large distances. This means that the properties of one particle can instantaneously affect the properties of another, no matter how far apart they are. This concept was first introduced by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935 in what is known as the EPR Paradox. The EPR Paradox was an attempt to show that quantum mechanics was incomplete. Einstein and his colleagues proposed a thought experiment to illustrate that if quantum mechanics were correct, then it would lead to spooky action at a distance, which seemed to violate the principles of locality and realism. Locality is the idea that objects are only directly influenced by their immediate surroundings, while realism is the belief that physical properties exist independently of measurement. Quantum entanglement appeared to challenge these fundamental principles of classical physics. In quantum mechanics, particles such as electrons and photons can become entangled through various processes, including spontaneous parametric down conversion, which occurs in non-linear optical processes, or through the interaction of particles in close proximity. Once entangled, the particles share a common wave function, which describes their combined quantum state. When a measurement is made on one of the entangled particles, the wave function collapses, and the state of the other particle is instantly determined, regardless of the distance between them. The implications of quantum entanglement are profound. One of the most significant is the potential for quantum teleportation. Quantum teleportation is a process by which the state of a quantum particle can be transmitted from one location to another without physically moving the particle itself. This is achieved by using a pair of entangled particles as a communication channel. When the state of the particle to be teleported is entangled with one of the particles in the pair, the state can be transferred to the other particle, effectively teleporting the quantum information. Another important application of quantum entanglement is in the field of quantum computing. Quantum computers leverage the principles of quantum mechanics to perform calculations at speeds unattainable by classical computers. Entangled particles can be used to create qubits, the fundamental units of quantum information. Qubits can exist in multiple states simultaneously thanks to a property known as superposition. When entangled, qubits can perform complex calculations through quantum parallelism, potentially solving problems that are currently intractable for classical computers. Quantum cryptography also benefits from the principles of entanglement. Quantum key distribution, QKD, is a secure communication method that uses entangled particles to create encryption keys. Because the properties of entangled particles are intrinsically linked, any attempt to intercept the key would disturb the entanglement and be detected, ensuring the security of the communication. This offers a new level of security, crucial for protecting sensitive information in industries such as banking, government, and healthcare. Despite its many potential applications, quantum entanglement remains one of the most mysterious aspects of quantum mechanics. Numerous experiments have been conducted to test the principles of entanglement and its implications for our understanding of reality. One of the most famous is the Bell test experiments, which measure correlations between entangled particles. These experiments have consistently supported the predictions of quantum mechanics, demonstrating that entanglement is a real and measurable phenomenon. To understand the full implications of quantum entanglement, It's essential to grasp the basics of quantum mechanics. At its core, quantum mechanics describes the behavior of particles at the smallest scales. Unlike classical mechanics, which operates under the assumption that particles have definite positions and velocities, quantum mechanics introduces the concept of probability. Particles exist in a superposition of states until they are measured, at which point the wave function collapses and the particle assumes a definite state. The Heisenberg uncertainty principle is another key concept in quantum mechanics. It states that it is impossible to simultaneously know the exact position and momentum of a particle. This principle has profound implications for our understanding of reality, suggesting that, at a fundamental level, nature is inherently probabilistic rather than deterministic. Quantum entanglement challenges our classical intuitions about space, time, and causality. In a classical world, objects are only influenced by their immediate surroundings, and information cannot travel faster than the speed of light. However, entangled particles appear to communicate instantaneously, regardless of the distance between them. This phenomenon has led to various interpretations of quantum mechanics, including the many worlds interpretation, which posits that all possible outcomes of a quantum measurement exist in parallel universes. The concept of decoherence provides a possible explanation for why we do not observe quantum entanglement in our everyday lives. Decoherence occurs when a quantum system interacts with its environment, causing the superposition of states to collapse into a single outcome. This process effectively hides the quantum properties of a system, making it appear classical. Understanding and controlling decoherence is a significant challenge in the development of practical quantum technologies. Recent advancements in experimental techniques have allowed scientists to create and manipulate entangled particles with increasing precision. For example, researchers have successfully entangled photons, electrons, and even large molecules. These experiments have not only confirmed the existence of entanglement, but also provided new insights into the fundamental nature of reality. One of the most intriguing aspects of quantum entanglement is its potential to revolutionize our understanding of space and time. Some physicists propose that entanglement could be the key to a deeper theory of quantum gravity, which aims to unify general relativity and quantum mechanics. According to this view, space-time itself may emerge from the entanglement of fundamental quantum bits known as qubits. This idea is still speculative, but it highlights the profound impact that entanglement could have on our understanding of the universe. In addition to its scientific and technological implications, quantum entanglement also raises philosophical questions about the nature of reality. If particles can influence each other instantaneously across vast distances, what does this mean for our concepts of cause and effect? Does entanglement suggest that the universe is fundamentally interconnected, with all parts influencing each other in subtle ways? These questions remain open to debate and are likely to be explored further as our understanding of quantum mechanics deepens. Alain Aspect and his colleagues performed a series of experiments in the early 1980s that provided strong evidence for the reality of quantum entanglement and helped to solidify its place in the world of physics. The EPR paradox suggested that there must be hidden variables that could explain the strange behavior of entangled particles. However, in the 1960s, physicist John Bell developed a theoretical framework known as Bell's theorem. Bell's theorem showed that no local hidden variable theories could reproduce all the predictions of quantum mechanics. In other words, if quantum mechanics were correct, then entangled particles would exhibit correlations that could not be explained by any classical means. This set the stage for experimental tests of Bell's theorem, and one of the most famous and crucial of these tests was conducted by Alain Aspect and his team. Between 1981 and 1982, Aspect performed a series of experiments at the Institut d'Optique in France to test the predictions of quantum mechanics against those of local hidden variable theories. In Aspect's experiments, pairs of photons were generated in a special process called spontaneous parametric down conversion. This process involves passing a laser beam through a nonlinear crystal, which splits some of the photons into pairs of entangled photons. These entangled photons were then sent in opposite directions to two separate detectors located far apart from each other. The detectors were equipped with polarizers, which could be set to measure the polarization of the incoming photons at different angles. The key idea was to measure the correlations between the polarization states of the entangled photons. According to quantum mechanics, the results of these measurements should exhibit strong correlations that could not be explained by any local hidden variable theory. Aspect's team used fast-switching devices to randomly change the settings of the polarizers during the flight of the photons, ensuring that the choice of measurement settings at each detector was truly independent of the other. This was crucial to rule out any possibility that the detectors could influence each other in a classical way. The results of Aspect's experiments were clear and compelling. The correlations between the measurements of the entangled photons violated Bell's inequalities, a set of mathematical inequalities that must be satisfied by any local hidden variable theory. Instead, the results matched the predictions of quantum mechanics, providing strong evidence that entangled particles do indeed exhibit non-local correlations. Aspect's experiments were a major milestone in the study of quantum entanglement. They provided the first clear experimental evidence that the strange predictions of quantum mechanics were correct and that entanglement was a real and measurable phenomenon. These experiments not only confirmed the existence of quantum entanglement, but also helped to establish the foundations for the development of modern quantum technologies, such as quantum cryptography and quantum computing. Following Aspect's groundbreaking work, many other experiments have been conducted to further test and explore quantum entanglement. These experiments have used various types of particles, such as electrons and atoms, and have employed increasingly sophisticated techniques to test the limits of quantum mechanics. In every case, the results have consistently supported the predictions of quantum mechanics and the reality of quantum entanglement. For instance, in the late 1990s, researchers at the University of Innsbruck in Austria, led by Anton Zeilinger, performed experiments with entangled photons over much greater distances. They successfully demonstrated entanglement over several kilometers, further confirming that the phenomenon was not limited by distance. In 2015, a series of loophole-free Bell test experiments were conducted, addressing potential weaknesses in previous experiments. These tests, performed by various research teams around the world, closed all known loopholes and provided even stronger evidence for quantum entanglement. One notable example is the experiment conducted by a team at Delft University of Technology in the Netherlands, which used entangled electrons in diamond to perform a loophole-free test of Bell's theorem. These experiments collectively reinforce the understanding that quantum entanglement is a fundamental aspect of nature, challenging our classical intuitions about space, time, and reality. They have paved the way for new and exciting advancements in quantum science and technology, promising a future where quantum mechanics plays an even more central role in our understanding of the universe. As scientists and engineers continue to harness the power of quantum entanglement, we can expect to see a wide range of revolutionary advancements. One of the most promising applications of quantum entanglement is in the field of quantum computing. Traditional computers use bits, which can be either 0 or 1, to process information. Quantum computers, on the other hand, use quantum bits or qubits. Qubits can exist in multiple states simultaneously due to a property called superposition. When qubits are entangled, they can perform complex calculations at unprecedented speeds. This capability has the potential to revolutionize fields that require massive computational power, such as cryptography, drug discovery, and material science. In cryptography, quantum entanglement offers a new level of security through quantum key distribution, QKD. QKD uses entangled particles to generate encryption keys that are shared between two parties. The unique aspect of QKD is that any attempt to intercept the key will disturb the entanglement, alerting the parties to the presence of an eavesdropper. This ensures that the communication remains secure. Quantum cryptography could protect sensitive information in industries such as banking, government, and healthcare. Quantum entanglement also holds promise for advancements in quantum communication. Traditional communication methods rely on signals that travel through cables or the air, which can be slow and subject to interference. Quantum communication, however, can transmit information instantly over vast distances using entangled particles. This could lead to the development of a global quantum internet, enabling ultra-fast and secure communication across the world. In the realm of sensing and measurement, quantum entanglement can enhance the precision of measurements beyond what is possible with classical systems. Quantum sensors use entangled particles to achieve extremely high sensitivity, making them useful for applications such as gravitational wave detection, navigation, and medical imaging. These sensors could lead to significant improvements in fields ranging from astronomy to healthcare. Another exciting application of quantum entanglement is in quantum teleportation. While teleportation of matter as seen in science fiction is still far from reality, quantum teleportation of information is possible. Quantum teleportation involves transferring the state of a quantum particle from one location to another using entangled particles. This could be used to create highly secure communication networks and improve the efficiency of quantum computing systems. Looking to the future, one of the most ambitious applications of quantum entanglement is in the development of quantum networks. These networks would connect quantum computers and other quantum devices, allowing them to share information and resources. Such a network could exponentially increase the computational power available for solving complex problems and lead to new breakthroughs in science and technology. In addition to these technological applications, quantum entanglement also has potential industrial uses. For example, quantum-enhanced imaging techniques could improve the resolution and accuracy of imaging systems used in manufacturing and quality control. Quantum metrology, which uses quantum entanglement to make precise measurements, could be applied in industries such as aerospace, where extremely accurate measurements are critical. As research and development in quantum technologies continue to advance, we can expect to see even more innovative applications of quantum entanglement. These advancements have the potential to transform various industries, leading to new products, services, and capabilities that were previously unimaginable. However, it is important to note that many of these applications are still in the experimental stage and face significant technical challenges. Developing practical quantum technologies requires overcoming issues related to stability, error correction, and scalability. Nevertheless, the potential benefits of quantum entanglement are so profound that researchers and industries are heavily invested in solving these challenges. The field of quantum mechanics, particularly quantum entanglement, is ripe with potential for future research. As scientists continue to unravel the mysteries of the quantum world, several exciting directions and questions are emerging. One major area of future research is improving the stability and coherence of quantum systems. Quantum bits or qubits, which are the building blocks of quantum computers, are highly sensitive to their environment. This sensitivity leads to a phenomenon known as decoherence, where the quantum state of the qubits gets disrupted. Researchers are working on developing new materials and methods to protect qubits from decoherence, which is crucial for building reliable and scalable quantum computers. Another important direction is the development of error correction techniques for quantum computing. In classical computing, error correction is straightforward, but in the quantum realm, it is much more complex due to the nature of quantum states. Scientists are exploring various quantum error correction codes that can detect and fix errors without destroying the quantum information. This research is essential for making quantum computers practical and useful for real-world applications. Quantum communication is another promising area of research. While quantum key distribution, QKD, has already demonstrated secure communication using entangled particles. Extending this technology to create a global quantum internet is a significant challenge. Researchers are investigating ways to transmit entangled particles over long distances without losing their quantum properties. This includes developing quantum repeaters and satellite-based quantum communication systems. Entanglement swapping is a fascinating concept that allows the entanglement of particles that have never interacted directly. This technique could be crucial for building large-scale quantum networks. Future research will focus on perfecting entanglement swapping and integrating it into quantum communication protocols to enable more robust and flexible quantum networks. In the field of quantum sensing and metrology, scientists are exploring how to use quantum entanglement to achieve unprecedented levels of precision in measurements. Quantum sensors could revolutionize fields such as navigation, medical imaging, and environmental monitoring. Research is ongoing to develop practical quantum sensors that can be deployed in real-world applications. Quantum simulation is another exciting research direction. Quantum simulators use controllable quantum systems to model and study complex quantum phenomena that are difficult to investigate directly. These simulators could provide insights into new materials, high-temperature superconductors, and even biological processes. Future research will focus on improving the capabilities and accuracy of quantum simulators. Understanding the fundamental nature of quantum entanglement and its implications for our understanding of reality remains a central question in quantum mechanics. Researchers are exploring various interpretations of quantum mechanics, such as the many worlds interpretation and the role of quantum information in the fabric of space-time. These studies could lead to a deeper understanding of the universe and potentially new theories that go beyond our current framework of quantum mechanics. Quantum machine learning is an emerging field that combines quantum computing with artificial intelligence. By leveraging the power of quantum computers, researchers aim to develop new algorithms that can solve complex problems more efficiently than classical algorithms. This could have a significant impact on various industries, including finance, healthcare, and cybersecurity. Future research will focus on developing practical quantum machine learning algorithms and demonstrating their advantages over classical methods. Finally, there is a growing interest in exploring the ethical and societal implications of quantum technologies. As quantum computing and communication technologies become more advanced, they will have profound effects on privacy, security, and the economy. Researchers are beginning to consider the ethical implications of these technologies and how to ensure that their development benefits society as a whole. The field of quantum mechanics and entanglement is full of exciting research opportunities. From improving the stability of quantum systems and developing error correction techniques to exploring quantum communication, sensing, and machine learning, the future of quantum research is bright. As scientists continue to push the boundaries of our understanding, we can expect to see groundbreaking discoveries that will shape the future of technology and our understanding of the universe. Thank you for joining us on this journey on quantum entanglement. Please like, comment, and share the video, and please do not forget to subscribe for more videos.